All right. Welcome, everyone. I hope the remaining can find somewhere to sit. My name is Mikkel Larsen. I'm a software engineer at Zalando. And today I want to talk about how we in Zalando continuously deliver our Kubernetes infrastructure, and hopefully also give you some ideas of how you can do it. I've been working with Kubernetes for the past 2 years almost at Zalando, so not so much building Kubernetes core or anything like this, but more operating it and building controllers and things around it to be able to operate it in a reliable way at a fairly large scale. And some of you might not know Zalando. I guess since we're in Europe now, more people will know it, but you might be wondering why we have shoes, why I have shoes on my slide. But to give you some context, Zalando is the biggest fashion online retailer in Europe. We have a revenue of 4.5 billion euros as of 2017, and we have 15,000 employees in Europe, and we are spread over a number of countries in Europe, and we have 2,000 million visitors per month, and fairly large. Out of these 15,000 employees, around 2,000 are in the tech department or working with tech within Zalando, and this translates roughly to a little over 200 delivery teams. And I work in a team that is responsible for the Kubernetes infrastructure and also the AWS infrastructure. And to support all these teams, our current scale looks like this. So we have 366 AWS accounts, and we have 84 Kubernetes clusters as of this morning. And you might think 366 AWS accounts, it seems like quite a lot. One of the reasons is that we come from a model where we gave one AWS account per team, more or less. Maybe some teams even got multiple AWS accounts for staging, testing, production, and so on. We have this tool set around AWS we call STUPS, which is what the infrastructure we are transitioning from. It's just some tools to help making the AWS services a bit easier to use, but it's pretty much vanilla AWS. You can think of it this way. And in this model, we have, like I said, AWS accounts per team. We have some rules that all instances must run with the same AMI for compliance reasons, so all teams must use the same AMI, and they therefore also have to update this AMI at some point. Everyone gets power user access, so like not exactly root, but almost to the AWS account, so they can pretty much do whatever they want, which gives them a much power, but with power comes responsibility, of course, and there's a lot of responsibility if you have to manage everything for every team, that every team has to do this. So basically, the rule is you build it and you run everything. And everything means also monitoring. So we, of course, have a central monitoring system at Zalando, but to actually get monitoring for your services, you would have to deploy something into your AWS account, like an agent that can pull data from different services that you run. And this you have to manage yourself, that this agent is running. Same with CI/CD, we also provisioned Jenkinses for each team if they wanted to, but they had to kind of manage this themselves. So we're transitioning to a model where we provide Kubernetes as the base infrastructure, and then we build a bunch of stuff on top of this. So we have, instead of having one Kubernetes cluster per team, something like this, we have now clusters per product. And product is multiple teams, so 3 to 6 teams, depending on how big the product is. And then the reason why we don't just put everything in one cluster or something like this is that you have an organization that is structured in a certain way, and you have to like do it gradually. And of course, there's also like reliability issues with putting everything in one cluster, but that's a different thing. And one of the benefits here with Kubernetes, for our case, is that the teams no longer have to manage the infrastructure at the OS level. So the instances are managed by our team, and we update the AMI that we use for the Kubernetes nodes, and they don't have to care about this. And instead of giving everyone production, like power user access to production, we use a hands-off approach, which basically means that in production Kubernetes clusters you don't have write access, so you can read everything, but you can't just do kubectl apply or exec or something like this to get into your container or delete something. You can do it in case of emergencies, of course. You can request privileged access, but by default you don't get this. And then we also provide a lot of stuff out of the box. So like I was talking about the monitoring stuff, this we provide automatically in the cluster when we provision them. The CI/CD solution is something we have that is integrated with our Kubernetes setup, which is more or less out of the box when people create a repository for a new application. And just to be clear, what I'm talking about, or what I want to talk about today is not like CI/CD onto Kubernetes, but actually continuous delivery of the Kubernetes infrastructure. And when we started to set up this whole Kubernetes infrastructure about 1.5 years ago or so, we had some kind of philosophy. I think philosophy is maybe a too big word, but just to have some idea of what do we want with this platform and how should it kind of work. So one thing is that we don't want to have any pet clusters, meaning we don't want to manage 80 clusters individually because some teams have a very special need in this way and we only deploy the monitoring for them and others have some other monitoring solution or whatever. It should be fairly generic across all the clusters because then it's much easier to manage from us. Of course, there will be differences in what instance sizes the teams need for the different services. So these things, of course, we can tweak on the cluster level. But most things we try to keep as generic as possible, at least for the base cluster setup that we provide. Another thing was that we wanted to always provide the latest stable Kubernetes version, meaning right now we have 1.9 instead of 1.10, but this is just not there yet for us. And we actually transitioned the older cluster we created, the first one, we transitioned from 1.4 all the way to 1.9, so updating all the major versions in between. And this is a bit different from like GKE or the Azure Kubernetes service, where you kind of, as a user, you can choose to update to which version when it fits you. But in our case, we kind of take the responsibility of updating this for our users, and we make sure that we test it enough before we roll it out. And then we kind of just roll it out when we are sure there's no disruption that can happen. Almost sure, right? And then they don't have to care about it, because if you ask your users or 80 products to care about when to update, then you will see that they probably won't update because it's safer to, or it's easier to just let it run as it was. And of course, with this being able to provide the latest version always also means that we want to do it in a continuous and non-disruptive way with the cluster updates. So from the beginning, we didn't want to have any maintenance windows, that we only do cluster updates on night, because then we can maybe be unavailable for a while and then it's fine. We wanted this to be something that we can do all the time. Also, because if you have security issues, you want to be able to roll it out right away. You don't want to wait a week because you have a maintenance window in the weekend only. So building the infrastructure from the beginning in a way that it can just be rolled out whenever makes it much easier when you really need to do it. And we also think about, like, we do cluster autoscaling of our clusters, and if you think about rolling all the nodes in a cluster or doing scale up and scale down, it's not so much different what is actually happening to the things that are running inside the cluster. So it should work. And then another thing was to be fully automated operations. Again, it's in quotes because I think everyone knows who does operations that can't be fully automated. This is the ideal situation is that we can just make a pull request to our configuration repository with some change, and then we just click merge, and then we just see everything roll out. And this also works for the most time, but of course sometimes you have to do something manually. But this is the philosophy anyway. to give you a bit of context about our setup that I'm talking about. Doesn't mean that you can't take these ideas that I'm presenting today and not use it in a different environment, just to give you the context for how we're running it. We provision our Kubernetes infrastructure with, we run it on AWS and provision it via CloudFormation. We run etcd outside of the masters, which is, I mean, it's a common approach to have etcd on the master nodes, but we take it outside and have a separate stack for this. And this is just to make it easier to, like, the masters become stateless in this case, and it's very easy to have a highly available master setup where we don't have to care about etcd when we do updates of the masters. We use container Linux for the nodes, and we treat it kind of like an immutable instance or node. So we don't use the feature of like auto updating of container Linux. We just, if we want to update the nodes, we just replace it with a new one. We also deploy our nodes in multiple availability zones. So basically an auto-scaling group in AWS, if you're familiar with that, that spans multiple availability zones. And this is to make our, whatever our users deploy automatically be resilient to availability zones being down and so on, which also, of course, brings some problems because you have volumes and so on that are tied to one availability zone. Then we have HA, high available control plane, which is, like I said, stateless because we don't have the etcd, and we have an ELB in front where we terminate SSL, and then we can just roll the master nodes behind this if we do an upgrade of any kind. Our cluster configuration is stored in Git, and we actually have it on github.com, our production configuration. If you want to check this out, I have some links later on. And we run end-to-end test via Jenkins setup, end-to-end test against the clusters that we create. And then changes are rolled out via something we call the cluster lifecycle manager, which is like a controller component that knows how to, first of all, apply this CloudFormation in the right way. Our configuration has some Go templating for simple substitution of values, and it does this kind of stuff. And then it also has it knows how to update the nodes in a reliable way. And this cluster lifecycle manager is open source since Friday, so you can go check it out on our GitHub. It's still in a state where it's a bit Zalando specific, but we want to work on it to make it more generic, that is useful without too many assumptions. So we have also something that we call the CLUSTER-REGISTRY, which is either HTTP REST API in our setup or just a YAML file. But basically the format looks like this. You have a list of clusters with the ID, the URL for the API server, some configuration items, which are usually unique per cluster. Could be some keys in there for secrets for our logging agent or whatever that we encrypt and store there. Has an environment, a region, lifecycle status. And the lifecycle status is used by the lifecycle manager to know if it should create a cluster, or if it's already created, or if it should decommission a cluster, and so on. And then we have a list of node pools, as we call them, which is, I think they also use the term node group in GKE, for instance. But it's basically, in AWS terms, it just translates to an auto-scaling group, in our case, where you just specify, I want a set of nodes that are identical, that have this instance type, that have this name for the node pool. There's a min and max size, and then it can auto-scale between these sizes. And we can have multiple node pools defined. Our cluster configuration this is the one on GitHub, which is roughly looks like this with a cluster YAML, just the CloudFormation spec basically of the cluster setup, and then we have the etcd CloudFormation stack, and then we have a folder called manifest, which is all the Kubernetes manifest that we deploy as default. So all like flannel daemon set for our overlay network and our monitoring system is deployed just by putting a YAML file, a Kubernetes YAML file in this manifest folder. And then we have this master and worker cloud container Linux configuration, which is just like the user data of the EC2 instances. So how to start kubelet and how to bootstrap things on the nodes. This is what we configure in these files. Yeah, and then we have this, like I said, the lifecycle manager. So how it works is, I tried to pinpoint it here. So it has two sources of configuration. It has the Git repository where we have our cluster configuration, and then it has the cluster registry which has this metadata about the clusters. And it basically watches both of these configuration sources, and if there's a change to one of them, it will react on this, merge the information together depending on the cluster. And in the beginning, if it's a new cluster, it will create it by do a create with CloudFormation, create a new CloudFormation stack for etcd and one for the Kubernetes infrastructure. And this will basically set up this where we have the Kubernetes API server, usually behind the ELB with multi masters, and then we have the worker pool of nodes deployed. And once this is deployed, and when you're creating a cluster, it will basically wait for the API server to respond, so it knows it's there. And once it's available, it will start to apply all the manifest that we have defined in this manifest folder. So deploying all the things that we run in the kube system namespace in our case. So all the cluster components basically. And if you already have the cluster created and there's just an update, then it will just reapply the CloudFormation stack. AWS will then update whatever the component that was changed there, and if there's no changes, it will not do anything. But then it will also apply all the manifest again. This it will do every time to synchronize. So even if you go and delete something in the cluster, on the next update, it will be overwritten and have the actual configuration that we have stored in Git, which is tracked and it's easy to see what is actually running in this cluster. And the way we kind of feed new configuration into the cluster is we have this kind of upgrade flow where we will usually create a branch with my new feature. Then we make a PR. We add a ready to test label on the PR when it's ready to be end-to-end tested. And then once it's ready, we either add a label ready to merge, or we just merge it. And then we merge it into something we call the dev branch. So the reason we have these branches is that we kind of created this idea of channels. So our clusters live in different channels. So we have dev, alpha, beta, stable, and so on. We can just create a new branch to create a new channel level. And then it kind of flows from dev to alpha to beta to stable and so on, the changes. And ideally we wanted to have it like you just merge to dev, and then after some time, after some monitoring has happened and there's been no issues, it automatically can follow it into alpha and beta. We're not there yet. We are still doing it manually, so creating a new PR for the next branch. But this is something we want to work on to actually fully automate this part, because it's a bit annoying to. It's at one point it's a bit of a safety feeling that you don't do it automatically, but at the other point, if we already have it end-to-end tested and so on, we should just be able to move forward. So actually we only have 3 channels right now, which is dev, alpha, and beta. And the way we have chosen to structure this right now is that we have the dev channel with 3 clusters, which are development clusters, meaning that these are used by people to deploy test applications and so on, but they are not like production critical or anything. But there's enough people using them to actually notice if something that we merge in a new configuration change, to spot that there might be something wrong that we have to look at. Next, we have the alpha channel, which right now we have our main infrastructure cluster there, which is basically what my team and surrounding teams are using to deploy all the infrastructure that we need to, that all our teams need to integrate, and CI/CD system, and all this is running there. And the reason we have it already as the alpha is that it's very important to us. So if something happens, we will notice it right away, or be woken up at night by this. And On one side, this is good because we can notice things right away and fix it. On the other side, if we break something, we really break something. But that's kind of the trade-off we've made right now. We might change it at some point, but that's at least the reasoning behind. And then the last channel is the beta, which beta or stable it could be called. Doesn't really matter. It's just all the remaining clusters for the products that are there. So if we see that everything is working in alpha, then we are fairly confident that the beta clusters will also work when we roll out an update. And this is right now, 80 clusters. Like I said, we do end-to-end test on every PR. Basically looks like this from the GitHub point of view. So we have these 3 orange parts that are running different end-to-end tests. And the end-to-end tests we run are the conformance test suite directly from upstream Kubernetes. So there's this whole test/E2E in the Kubernetes repository, where there is like almost maybe thousands of different test cases, end-to-end test cases. And currently there's 144 of those are conformance tests as of 1.9. And these we run to like get a general sense of, is the cluster performing in like a conformant way? This is also the tests that are run by this Sonoboy for validating clusters that are these certified clusters. So it's the same test suite. I think we even run a bit more than there. Next, we also pick some stateful set tests. These are not part of the conformance because they require some default storage class configuration in the cluster, which is not required by the conformant part. So we pick these out individually, and we pick out 2, and these are really good because they test stuff like attaching volumes to a stateful set. So I think we run the Redis, like a Redis, deploying a Redis 3-node Redis cluster, and then each node needs a volume, and in AWS this means an EBS volume, so we're actually testing the full end-to-end of the controller manager being able to schedule an EBS volume, attaching it to the nodes, kubelet being able to mount the volume, and so on. This should just work from Kubernetes already, but we might misconfigure something on our nodes that would make it not work, so that's why we are testing this. And lastly, we have some, I call them Zalando tests, but it's just our test for our own tooling. So we have tests for our Ingress. We have a Ingress controller that's also open source that creates application load balancers for Ingress. And this we're testing. We also have this external DNS project, which is Kubernetes incubator project. So we're actually testing deploying an application with a pod, with an Ingress. Do we get a DNS name? Are we able to route all the way to the pod in the cluster? And then we also test some pod security policy stuff, which I think is more or less legacy now in our case, because it's also tested upstream now, but it wasn't when we introduced it last year. And the way we, the way we run the end-to-end test is that we think that you want to do an upgrade from the dev channel to alpha. You want to move all the things that are new in dev into alpha. Then we basically have a Jenkins pipeline where we first create a cluster based on the alpha branch, because it's like the base branch. Then we do a cluster update using our cluster lifecycle manager from the dev branch. So we take all the changes from dev to alpha, the dev there, and apply these. And the reason we do this is that if we just create a cluster directly from the dev branch or from the merge between alpha and dev, then we just test creating a new cluster from the new configuration. And this might work perfectly fine. But what we also want to test is that we are actually testing doing a live migration from one, maybe it's one Kubernetes version to a second one. We actually want to test that this flow also works, that the resulting cluster is also running correctly. Once we have this cluster set up based on the dev changes, then we basically run the end-to-end test, the conformance test, the stateful set test, and the Zalando test. And we create one cluster per test case, or per these 3 tests. So we create 3 clusters in total. And this is just to speed it up. If one of them fails, then you would have to like wait for for a long time to rerun all the tests if they were in one cluster. If only one of the tests fails here, it's only one cluster we have to restart, and the other tests we don't have to rerun. If everything works, we just delete the clusters again to save cost. If everything doesn't work, we leave the clusters running there for a little while, because then we can go and inspect and see if there's something wrong with the cluster or what happened. It's easier than looking at the logs to actually do this. From a Jenkins point of view, it just looks like this. I think this one, it takes like 20 minutes here to set up the cluster and update it. But it of course depends on how many changes we make. And the integration test here are the Zalando ones, which takes like 10 minutes to run, mostly waiting for DNS and stuff. So it takes like 40 minutes or so total. And looking at the output of the end-to-end test looks something like this. This is 144, this is the conformance test, and it says that it skipped a bunch, so 638 were skipped. And this is because you can, this is how you run the test basically. I created this image where it's just pulled out the end-to-end test from the upstream Kubernetes and only packed this into one image, so you don't have to have the whole Kubernetes, which is much bigger. I just put this for if anyone is interested. But basically it just runs the end-to-end tests that are upstream Kubernetes. It has some flag. -p means parallel, focus means what you want to focus on, and skip what you don't want. So you want to focus here on conformance. So each test has this naming convention that it has this square bracket and then some value that you can target with a regex basically. And then we just skip the serial, which cannot be run in parallel, so they have to run one by one. So, and these we don't need. It take a long time, so we skip these. The stateful set, similar. You just pick another thing to focus on, stateful set basic here, and stateful set, the one with the redis. And pretty much you can, if you find some test that would test something good for you, you can just pick it out and use that this way. A few hints for running end-to-end tests that we found is that it's possible to run with flag attempts. This is a flag to the test orchestration thing. It's called Jinko, some Go test framework. But flag attempts basically means that it will, if the test first fails, then it will actually try to run it again. And this is useful because some of the tests are just creating a pod or creating multiple pods. And since our cluster is auto-scaling during the test, we might lose a pod because the tests are not really built in a reliable way. So having the flag attempts too usually is enough to make sure that it's working. And what we're testing is that our cluster setup works, not that the end-to-end tests are reliable or something. So that's why it's fine. And then another idea is to update the end-to-end image for every major release you do. You roll out, so going from 1.8 to 1.9, you want to also change the end-to-end image you use. But going from 1.9 to 1.9.1 is usually fine. That's what we found. Disable broken tests we skip. Sometimes some tests are just broken in a Kubernetes release and you want to skip them. And then remove all completed pods from the kube system namespace. So the end-to-end test always check that the kube system namespace everything is running in there. And even if you have like a cron job that creates a completed pod, then it will fail to run. So you also want to make sure these are removed. Okay, so this was the end-to-end part. The really interesting part is actually upgrading the nodes, because one thing is just creating a cluster, updating it, running end-to-end tests, but if you don't have anything running inside, you don't really know if the upgrade went really well in between. So first we went with a naive approach, I call it, where we basically just have an auto-scaling group. We set a fixed number of we just fix the number in the auto-scaling group when we want to do an update, so we kind of lock it so it can't auto-scale, and then we just do the current +1, so we get one extra node, and we basically just wait for AWS to bring up this extra node. Then we drain a random node in the cluster, and this will then terminate it, and AWS will bring up a new one because you then removed one and the desired is less than, the current is less than the desired. And this you do again for all the nodes. And this was of course fine. There was no issues with this at all, and our users were very happy. Almost. There was a few problems. One problem is that we didn't have any like time between draining nodes, so we didn't have any specific time interval between when can we go to the next node. So we just drained, and then how long do we even wait? It was not clear. Another problem was that the volumes, like I already said, are per availability zones. So if your pod that needs a volume in one zone, it can't get scheduled to a different node. So if you don't have enough nodes in a particular zone where you have the volume, then you're out of luck. Your pod is just pending and you can't really move forward. And since we didn't have any timer, we just eventually removed the next instance where another pod of the same application might have been running, basically killing everything at once. Another problem was that we fixed the auto-scaling group size, so we could basically not scale in and out in between the upgrades. So we were kind of fixed, and we would have like pending nodes from the autoscaler, which we would have to wait until after the upgrade to actually scale out, which is not good if people are deploying a lot. And a fourth problem was that how do we actually handle stateful applications? So in our case, PostGRES is used, and if you have the case where you have a master pod and some replicas, then how do you know if you do this to drain one node? You don't know if you're actually draining the master. And if you're draining the master, then your PostGRES cluster becomes unavailable. So this is not the ideal way to go. So what we did was we thought, okay, we need to design a new upgrade strategy that is more robust to these issues. And the first thing that we thought about is, okay, what does it mean for a node to be ready? Which is important because then we can know when we can move on to the next one. So I think about the nodes as the Kubernetes node object and the underlying EC2 instance in our case, or VM or whatever. And if you split them up, the kubelet has this reporting node ready. So this is so easy to see if it's ready. And EC2 instance, if you run it in an auto-scaling group, you can kind of see if it's ready by, is it in service by, does AWS see it in service in the auto-scaling group? Another thing you can also do is you can check if there's an elastic load balancer attached to the auto-scaling group. Then you can see if the instance is also in service in this load balancer. And this is important for our master setup, because if we remove the masters too fast, then we might remove those that were in the load balancer, which we don't want. Another thing is something that Kubernetes actually provides. So this is pod disruption budgets, and this is a way to say that, in this case, min available 1, meaning that if I have 3 pods, then I can kill 2, and then I still have 1 available, and our infrastructure will not continue deleting more pods if this would disrupt the budget, basically. So you have a controller that evicts the pod. This is successful. It evicts the next one, successful, and then it tries to evict the third one. And since the budget would be disrupted if you were to remove the last one, then it fails. And then onto how to handle the PostGRES stuff. Basically, we have again this setup with the master and replica. We put these labels on the PostGRES pods, and then we have a PostGRES operator, which is also an open source project that our database team are developing. It's basically a way you can define a custom resource definition for a PostGRES cluster, and then it gives you a stateful set with these properties and manages the whole cluster for you. And say here in the case we want to drain the master, then the operator will put a pod disruption budget saying we always has to have 1 master pod available. So if you try to drain the master, it will basically fail the eviction. And then the PostGRES operator in the meantime will see that we are doing a cluster update. So we see the green node is a new node, and it will notice this. It will evict a random replica of the cluster, because this is fine, just a read replica. It will move this by being evicted. Kubernetes will automatically move it to a new empty pod node. And then the PostGRES operator will see, okay, now there's a replica on a new node. It makes sense to promote this to master. So it promotes this. And then we did a control failover. And the one that was the master before we can now evict because it no longer has this pod disruption budget that you can only that you have to have one master. This is already satisfied by having moved it there. And this would look something like this. So you have min available 1, and when you have a label role master, basic way to do it. Just to quickly summarize how this rolling upgrade of nodes looks. So we have a node pool autoscaling group. We have a bunch of availability zones. We have some instances there. We have, of course, the pods running on the instances, and we have this volumes, persistent volumes attached to each of these pods. And when we do an update, we basically find all the old nodes in the cluster. We put a taint, prefer no schedule. This is also a Kubernetes feature where you can say if there are nodes available without this taint, then prefer to schedule the new pods to these new nodes. And then we bring up 3 new nodes, because then we get 1 in each availability zone. And even if we don't get 1 in each, like if it's unbalanced in some way, then we actually wait till we have at least 1 new node in each availability zone. Because then if we move pods from an old node to a new one, then we always have, we will always be able to attach the persistent volume. So if we then drain a node, then Kubernetes will move the pods to something else, and the ones that have the persistent volume will stay in the same zone, but the others without a volume might go to a different zone. It could also stay in the same. And then Kubernetes will basically, or AWS will bring up a new instance, because we changed the value in the autoscaling group. And then, yeah, it basically continues from there. And the way we do it here is that we don't fix the autoscaling group size anymore. We just always find the old nodes. So even if we are in the middle of an upgrade and our controller dies, it will just start up again and find all the old nodes and continue from that. So autoscaling can happen. It will just bring up new nodes in the meantime, and then we actually have less work to do in the controller. Of course, there was a few times where this wasn't fine. I just wanted to mention, because you can always talk about how well it goes. And one thing was that we broke our overlay network in our main infrastructure cluster one time, because we wanted to switch from etcd as a backend for Flannel to using the Kubernetes objects as a backend for Flannel. And we, of course, wanted to do this live in a cluster that was running. So we planned for a while how to actually migrate between etcd and the Kubernetes as a backend, because Flannel has to know about the pod network, the IP space for each node, so it can actually route between the nodes. And if you just switch the configuration in the Flannel, then you would have some information in etcd and some in Kubernetes, and they wouldn't match. So our idea was to migrate this correctly. And this we failed to do. So basically we had on each node 2 different networks, one from etcd, one from Kubernetes, so the pods couldn't route anywhere because they had 2 mismatching networks. And the reason this happened was that we basically didn't test the upgrade path that I was talking about in our end-to-end test. We only created a new cluster from the new configuration, and this worked fine, but we didn't actually create an old cluster, update it, and then test. This would have caused this issue. Another one, just not really Kubernetes related or anything, it was just that we have our images on a Docker registry, internal one, and when we were confident at some point that we could roll out more clusters at a time, we had like 5 at a time we could deal with, then we thought that let's just remove this limit and do like 40 at a time, it doesn't matter, we are confident. Then we started to pull so many images from this registry that we basically took it down. And this was before we had this strategy where we checked if the nodes were ready or not. So we just kept rolling out new nodes that didn't get any kubelet running or anything. So yeah, we basically removed everything from the cluster, kind of. It was easy to stop the bleeding because we could just remove the controller because it's a single instance. So we just scaled it down to 0, and then everything stopped, and we could let the registry recover. Yeah, this is pretty much it. I just leave some links here for our open source project related to Kubernetes. And yeah, thank you very much.